Part B. Part B, we have the series x to the power k divided by square root of k squared plus 6k from 0 to infinity. To find the radius of convergence, by the ratio test, the series converges if the r equals the limit k approaches infinity, absolute value of k plus 1 divided by ak less than 1. Since the ak is the term x to the power k divided by square root of k squared plus 6, so the k plus 1 will be in the form of x to the power k plus 1 divided by square root of the quantity k plus 1 to the power second plus 6, and divided by k means multiplied by the reciprocal of the ak, or the square root of k squared plus 6 divided by x to the power k, and it must be less than 1 in order to be convergent. So simplify the expression. For x to the power k plus 1 is x to the power k times x to the first. So x to the k and x to the k will be reduced. Then we have the limit of the absolute value of the x multiplied by square root of k squared plus 6 divided by square root of the quantity k plus 1 to the power second plus 6, k approaches infinity less than 1. And then rearrange the term by leaving the absolute value of the x on the left and move the k and the limit to the right hand side. Then we get the absolute value of the x less than the limit k approaches infinity of the square root of the quantity k plus 1 to the power second plus 6 divided by the square root of k to the second plus 6, and the limit of the expression on the right hand side approaching 1. So we can say the absolute value of the x is less than 1, and 1 is the radius of convergence. Since r equals 1 is the radius of convergence, we can say that the series converges in the interval absolute value of the x less than 1, or x is between negative 1 and positive 1. Now we're going to check the two endpoints. For x equals negative 1, the series, the summation x as negative 1 to the power k divided by square root of k squared plus 6, k from 0 to infinity. This is alternating series with the ak equals 1 over square root of k squared plus 6. By alternating series test, number 1, we're going to check whether ak plus 1 less than or equal to ak or not, which is the test of the non-increasing. As we see, the numerator is 1, denominator is changing because of the k value. So then we can see this as the non-increasing terms for all k. And the condition number 2 of the alternating series test is the limit of the ak as k approaches infinity. The ak is 1 over square root of k squared plus 6. The limit of this term as k approaches infinity equals 0. So it satisfies the second condition, or we say it satisfies the both conditions of the alternating series. Therefore, the series converges at x equals negative 1. So we include the let n in the interval of convergence. Next, we're going to check at the other end. So for x equals 1, the series becomes 1 to the power k, which is 1, divided by square root of k squared plus 6, k from 0 to infinity. And this is the positive series that we can use the comparison test with the p series. As k approaches infinity, the term ak will become 1 over square root of k squared, which is the leading term of the denominator, or simplify this to be 1 over k. So by the comparison test, this series diverges because we compare with the p series with the p equals 1. With the condition that p is less than or equal to 1, the series diverges. So then we can say that the interval of convergence is negative 1 less than or equal to x strictly less than positive 1 with the radius of convergence r equals 1.